Welcome everybody to our event today. My name is Jason Grillo with AirMiners. It's wonderful to see you all here. We are working today on an event about DAC and Energy Systems. So we all know that energy is a critical component of getting direct air capture systems operational. What we're going to unearth today with a very interesting panel of guests is how the practical aspects of direct air capture in energy systems can work out for direct air capture startups, how we can anchor energy systems around direct air capture, and what it means for energy systems when more direct air capture facilities come online. To do that, we've got a fantastic, like I said, fantastic panel moderated by our own Adina Mangubat, who's our accelerator director in AirMiners. A little bit about logistics. We're going to start in with discussion for the first 40 minutes or so. Feel free to ask your questions in the chat, and we'll get to them at Q&A starting at maybe 40 or 45 minutes in. We'll continue recording until the top of the hour, then stop recording, and that will be the end of our main part of the event. If you want to hang on for networking afterwards for 30 minutes, I'm going to keep the Zoom line open so that we can chit chat and talk about what we learned during the course of our discussion today. So if you can't make the whole event, or if you have to duck out for whatever reason, we're going to have this put onto our YouTube channel in a couple of days. So you can re-record or you can review and share as you wish. With that, I just once more want to say thank you and hand the floor over to Adina Mangubat, our accelerator director. Adina.
Hello. All right, everybody. Well, let's get started. We're going to first have all of the panelists introduce themselves. We're joined by a very esteemed group of panelists today, and I'm very excited to have them all on board. So thank you again for making your time available. They're going to introduce themselves with 2 to 3 sentences about themselves, and then we're going to jump right into the topic discussion. So Grant, if you want to go first, followed by Rory, then Jesse, then Aniruddh.
Sounds good. Well, hey, everyone. Yeah, thank you for having me here. Grant Faber, founder and president of Carbon-Based Consulting. I conduct techno-economic and life cycle assessments for a wide range of carbon removal pathways, and I wrote a whole article on navigating clean energy procurement for carbon removal maybe several months ago. So super interested in this topic and looking forward to the panel.
Thanks, Adina. Hi, everyone. So I'm Rory, one of the co-founders of a London-based DAC company called AirHive. This year, we're building sort of 3 pilots, but 2 at the kiloton scale, and doing sort of early feasibility work for commercial facilities for 2025. So kind of very much a live topic for us about, how do we work out the energy system side of what we're doing.
Hi, I'm Jesse Jenkins. I'm an assistant professor at Princeton University, where I have a dual appointment at the Mechanical and Aerospace Engineering Department and the Andlinger Center for Energy and the Environment. And I run a research group called the Zero Lab, which Ani works with. And we do macro scale energy system modeling. So we're trying to understand how energy technologies fit together at the system scale, at a regional or national scale. And a big chunk of the work we do is focused on evaluating and understanding the role of emerging energy technologies and power generation and industrial decarbonization, direct air capture. And one of the big questions we've been grappling with is, what is this system level impact of direct air capture on the broader energy system as you add it to the mix? How does that cause indirect emissions impacts, either increases or decreases? And how do those impacts change as the types of technologies that we're considering, the configurations of the DAC plants, the energy sources that they're using, the operational strategies, et cetera? How does all that affect the system level impacts? So excited for this conversation. And Ani, I'll turn it over to you.
Thanks, Jesse. Thanks, Adina and Jason. So I'm Aniruddh Mohan. I'm a postdoctoral fellow at the Andlinger Center at Princeton. I'm working with Jesse and also Eric Larson at Princeton, looking at system-level impacts of direct air capture deployment. I'm an engineer by training, but most of my work now is interdisciplinary, combining engineering, economics, and policy to really understand the system-level impacts.
Right. Thank you for those effective and brief introductions so we can get into the meat of it. All right, so let's dive right in. I know that a bunch of the people that are on this call and that are going to be watching this recording are direct air capture startups themselves, right? And so I'd love to pose kind of an opening question that is very pragmatic in terms of its focus, which is, okay, so here I am. I'm a direct air capture company, and I'm trying to figure out how to operate a kiloton sized plant. What are the big pieces that I have to consider in order to get that up and running? So whoever would like to take the first kind of crack at that, what would you consider as you're trying to stand up a kiloton sized plant?
One of us is actually doing that. So Rory, do you want to take the lead on this one?
Sure. Yeah. I think so. I mean, the way we think about it is kind of two components to it. There is your technology development, and essentially all DAC startups are at their core technology innovators. And then there's the project development side. So, within the technology, if we're talking about energy systems stuff, rather than kind of, the sort of wider set of characteristics for sort of, kiloton scale pilots or even plants, you have a bunch of levers that you can pull on the technology side. So obviously you can play, there's things like how much the technology costs, in terms of capital equipment. You also have, how much energy is going to be required. And that's obviously something that a lot of DAC companies are really solving for, sort of cost and energy, those two core characteristics, plus, of course, how quickly you can kind of deploy it. The other things then, the sort of wider project development things, which we maybe call project delivery or development risks or challenges, are things that are less in your control, like the energy price that you pay. Also, can you get storage? What's the price of that storage going to be? And those are crucial because they do feed through into, into ultimately the cost per ton that you will be trying to sell your credits at. Other aspect of it is how clean is the energy, and that's crucial too, from a sort of life cycle perspective, because you sell on the net ton. So I think, in that development process, you can kind of go down two routes. You can say, we're going to do all of the project development ourselves. We're going to build out the solar farm or the wind farm. We're going to, work out how to also do the storage, even, that's maybe an extreme case, unlikely, but, you kind of conceptually, you can say, we'll do all the project development ourselves. We'll become a project developer. The other route, I think that, maybe just to say, that is likely to be rarer. Probably most people won't take that route, but it is a real pathway. And the merits are that you kind of have those first facilities within your own destiny to a substantial degree. I think the more likely pathway for most people to take is partnering. So that might be where you do project development, but you partner with an energy company, a storage company. It might be that you partner with a project developer and they take care of a lot of sort of energy and storage side. So in our case, the two pilots we're doing this year are with people that are project developers, where we sort of plug our technology in. It's a great way for us to demonstrate the technology at scale, in some cases being paid for upfront by the project developer, without having to take on too much of that. So we can kind of get our head down and focus on the development side, or sorry, on the technology development side. I think that's relevant then also for the sort of commercial facilities too. So, that dichotomy is, I think, a useful way of thinking about, you got to kind of work out where on the spectrum of that do you sit, and what does that imply about kind of your pathway, your sort of deployment pathway.
Maybe just to add to that, I think, one of the, of course, if you're at a kiloton scale, your main focus, right, is proving your technology works, driving improvements in design and efficiency, trying to get on a cost curve that gets you to a more economic place in the future. And so I would say in that sort of technology demonstration R&D kind of mentality, it is helpful to think beyond this kiloton scale out to where you want to be in 10 or 20 years. I don't think you need to worry about procuring electricity, today the way you're going to in 20 years necessarily, but there are potentially implications for how you might want to design your facility today so that in the future it is capable of operating in a flexible manner or integrating with clean electricity in a way that doesn't produce significant indirect emissions impacts. So I'm not going to, lose a lot of sleep over a kiloton, scale demonstration facility, potentially causing some indirect grid level emissions. But if we're going to be doing carbon removal at gigaton scale, I'm very much concerned about that. And so that's the work that we're trying to do in Zero Lab right now, is, think out to that future scale of at least 10 megatons, or, where we might be in the mid 2030s or ultimately hundreds of megaton scale, and think about how the operation of direct air capture systems of different designs might impact the electricity grid or the use of heat, from various sources that could be used for other opportunities. And there's a lot of parallels here in that analysis and thinking to the debates we've been having very rigorously around how to demonstrate that hydrogen electrolysis facilities are actually clean. So those of you in Europe or in the United States who may have been following these very heavily lobbied and vigorous debates that have to do with eligibility for subsidies for clean hydrogen production, how do you demonstrate that you're actually clean if you're plugged into a power grid where energy is sort of undifferentiated and it flows where it will based on the physics of the grid, not based on your contracts. And what we've seen in that context is that you can have very significant indirect emissions, even if your electricity consumption appears to be clean because you're buying renewable energy credits or purchasing 100% solar or wind power. The mismatch in timing between when you're consuming electricity and when the clean resources that you're supporting are generating electricity can lead to second order effects on the grid that may keep a coal plant running longer than it would otherwise, or may increase our reliance on natural gas in the evening to compensate for the decline in solar power. And so these requirements are coming, I think, into the fore for hydrogen because it's, likely to scale to a several billion-dollar, kind of industry very quickly. I think, direct air capture could scale quickly, but I think it's in an earlier, more technology nascent state. And so we have a bit more time maybe to get those rules and procurement guidelines right. It's also a lot more driven by voluntary action, and, voluntary actors have different goals. Like they're buying carbon removal contracts today for different reasons. Some of them are trying to focus directly on the emissions offsets. Others are much more concerned about having a catalytic role in driving the market forward and ensuring that 10 years from now, these are mature technologies. And so depending on your goals, as a off-taker, you may, have different strategies and you may care differently about these impacts as well. And so all that's what we're kind of thinking about right now too. And I would encourage that to be in the back of your mind as you're thinking about scaling up your technologies as well.
One thing I would add on the cost side is that paying a premium for clean energy today might not matter so much on an emissions perspective if you're just a kiloton plant. But it's something that you can possibly do because your capital costs are so high. So it's still a minor fraction of your total cost. Whereas in the 2030s, hopefully your capital costs have come down and now clean energy is also cheaper, either due to your efforts or because we have IRA, for example, in the US that is going to drive that reduction in cost for clean energy. So thinking about timescales in this and what percentage of your costs are going towards energy and how can you actually reduce the cost over time, but then also keep the emissions fixed, that's going to be important.
Go back and touch on some of the things you were speaking about, Jesse, with regards to design of the plant, given that you're not always going to have access to green energy all the time. And Grant, I know you spoke a little bit about kind of in preparation for this call about what you've been seeing in terms of operating variably, and I was wondering if you could just speak a little bit to that.
Definitely, yeah. So some designs are maybe some direct air capture designs are maybe a little bit more suited for ramping up and down, potentially in response to cheaper, intermittent, low carbon, like variable renewable energy resources. And so one could imagine a plant that is you have maybe an electrochemical back end, and maybe that is oversized, and maybe you run the adsorption or absorption unit consistently throughout the day because that's the part of the system that maybe requires a little bit less energy relative to the desorption/regeneration step. And then you ramp up the electrochemical back end to regenerate the sorbent to actually desorb the CO2 when maybe, it's the middle of the night and maybe in this certain geography, there's plenty of wind resources available at a low cost. So you can do that step then. So kind of, you would have like the fans blowing ambient air through the air contactor like all throughout the day, but then you would just be storing this carbonate in solution, just waiting for that time when you do have more low cost clean electricity. So the issue with that is, of course, that then your capacity factor is lower. So then your capital utilization is lower. So then you're going to have higher allocated CapEx costs per ton of CO2. And so it does become this trade-off. And I think, for different systems, I mean, that's where the role of techno-economic assessment comes into play, is to look at those trade-offs in different systems and think about how that might play out in different geographies that have different availability of low carbon energy resources. With all that said, if we do expect in 10 to 20 years to move to a grid that is 100%, like an electrical grid that is 100% low carbon all throughout the day, which we'll probably need, then maybe it does become less of a concern in 20 years.
Yeah, I think even in that future scenario, we're going to have pretty substantial differences in the cost of clean electricity. So hopefully we do have a 24/7 carbon-free grid. But what is going to be very true is that many of those hours, electricity is going to be really cheap, right? We're going to have a lot of wind and solar. It's very, its levelized costs are going to be, $20 a megawatt hour. Its marginal costs are zero. So a lot of times it's going to be producing power and willing to sell it for nothing, as long as it makes up enough money in other hours of the year. And so if you can flexibly consume intermittently available electricity in the future, or even in many parts of the world today, that's going to give you a real advantage in your cost inputs, for energy inputs. Now, again, today that maybe doesn't matter as much because while DAC is, many of the DAC processes are energy intensive, it's your capital costs that are really driving the cost of removal overall. But hopefully, as Ani said, those costs are going to come down as you get on experience curves and scale up your designs and repeatedly build them, and those costs of energy inputs become a more important factor. And one of the things we're exploring is the use of thermal storage for many of the processes that primarily most of the energy consumption is for thermal process heat requirements for sorbent regeneration or other uses. And it's pretty cheap to store heat, right? It's a lot cheaper to store heat than it is to store electricity. And so there's opportunities there to not necessarily change the design of your plant, but change the design or to couple that design with thermal energy storage technologies that can allow you to have basically a buffer between your consistent heat demand and the availability of intermittent, low cost clean electricity on the grid. We're seeing that strategy pursued in a lot of different sectors that need process heat, with companies developing high temperature or medium temperature thermal storage applications that can meet the kind of consistent process heat requirements of industrial facilities while tapping into that low cost clean electricity source. And I think that's going to be very analogous to many direct air capture systems, because even if you're technically capable of ramping your production up and down or using energy flexibly, the high capital costs mean you're going to want to use your kit at as high a utilization rate as makes sense. And so if you can kind of have the best of both worlds by sticking a big thermal battery in between that acts as a buffer and lets you, use intermittently available electricity and kick out consistent process heat, that can have real advantages. And that's one of the things that we're studying right now.
Yeah, really, really great, Jesse. I know that we did a little bit of talking about energy storage in the prep for this event. And so I just love to see and hear about what innovations are necessary to overcome challenges in energy storage, or what energy storage kind of vehicles are you seeing coming online that you think are going to be really relevant to direct air capture?
Do you want to tackle that?
I mean, most of the energy requirement is heat, not electricity. So just like Jesse said, I think thermal storage has a really big role to play, because if you're not doing thermal storage and you're not sort of storing that heat and using intermittent renewables, and you're not breaking up your system the way Grant suggested, you really need to hit a capital cost of around $100 per ton for it to make sense for you to run flexibly just on wind and solar alone, right? So having thermal storage in the system allows you to decouple, you can run the DAC constantly, but you can charge using intermittent renewables, which is low cost. That's at 95% efficiency to convert that to heat. So that can be really valuable. The other thing I would say is that, again, it really depends on the cost of that clean energy today versus 10, 15 years from now. For example, if you can couple with geothermal today, it might be expensive, but it's still a small fraction of your total DAC cost. 10, 15 years from now, that cost is going to come down. And then you have an opportunity to also think about how geothermal is on the grid and reducing emissions. So scope 2 is not just punitive, but can also be an opportunity to accelerate decarbonization. And it's the same with storage.
Let's talk about what this looks like, 10, 20 years out, because I know that, we started with okay, we're on the ground here today trying to sort out kiloton scale plants. But as we move to multiple megaton scale plants, the equation looks very, very different. And so if y'all could talk a little bit about what does the grid look like today? What is it going to need to look like? And what are the big innovations that have to come down the pipe in order for that future to be really viable?
Maybe I'll take a first stab. I mean, I think if we go to the mid 2030s, right, what we should see is a grid that is largely but not completely decarbonized. I think it's plausible that we'll have cut emissions in the electricity sector in the US by, 80% from current levels, maybe more. The average, the electricity mix might be 85 or 90% carbon free. And many, much of that, majority of that is likely from wind and solar power. And so, very low cost, zero marginal cost, but variable resources. We'll have a lot more energy storage in that system in order to help, take advantage of the regular price arbitrage opportunities that a system with lots of renewables has. Hopefully, we'll also have a lot more flexible demand that can shift around when it consumes to take advantage of that cheap electricity. So, for example, I, got to buy an electric vehicle a couple of years ago, about a year and a half ago. We've got a 280-mile range. That's enough for 5 to 7 days of driving. I can choose not only, what hours to charge, but what day of the week, to charge, right? And so that's a very flexible load, but there are lots of others as well. Hot water heaters can be wired up into aggregated loads, virtual power plants. Our HVAC systems could be more flexible. We could even be installing thermal energy storage in our buildings, right, to provide heating needs, which is one of the biggest consumers of electricity. And so heating and cooling needs. And so I think we're going to have a system that is, it's starting to adapt to this availability of clean, affordable, but intermittently available electricity. And I think that's the system that direct air capture is going to have to plug into. And so it's going to be an interesting, operational environment. Looks very different from today on average, although there are parts of the grid today, like say West Texas or parts of SPP, the Southwest Power Pool, Oklahoma or Kansas, that maybe look very much like that system already. And those may be some of the best locations in many ways, in many cases today, to start deploying direct air capture because of the very low cost variable renewables that you already have access to in those locations. So you could think about, if I'm trying to design a technology for that future grid, there's a great William Gibson quote, the future has arrived, it's just not evenly distributed yet. This is one of those cases where there may be parts of the world that actually look like the future already today, and you could think about doing some of your demonstrations in those locations to get used to that operating environment.
Maybe just touch quickly on that, Jesse. Yeah, and I mean, to take the UK grid at the moment, it's about 50% clean. Most of that is offshore wind. And actually, one of the constraints in the UK, and this might be sort of relevant for future DAC deployment, one of the constraints is that the transmission grid, it has bottlenecks. And so they are at times of the winter curtailing energy or curtailing offshore wind off the off the Scottish coast, because there's, most of the demand is where the people are, which is down south or in England, and they simply can't move all of it down. And so actually, I think it's a sort of interesting point here about, can DAC soak up otherwise curtailed demand? And, it comes back to the point that we talked about earlier, if you bring sort of upsize your capital costs, if you can bring down the energy price in such a way that it nets out without changing the price of so ultimately the per ton cost at all, or even, maybe marginally, I think there are interesting opportunities there for sort of DAC to plug in where there is still, let's say, unevenly distributed transmission grids, and it's sort of, and how actually the sort of renewable energy, generation plants, farms are rolled out at a particular time.
And if I can add on real quick there, just in terms of an innovation from like the LCA and MRV and like protocol development side, just as maybe we're seeing with water electrolysis, where there would be a phasing in of so-called 24/7 carbon-free energy procurement requirements, which require a degree of temporal and geographic matching and additionality to ensure that new loads added to the grid are are actually compensated for with low carbon energy. It might be easier in that future context due to developments in like the energy attribute certificate market that are maybe generating renewable energy certificates or guarantees of origin that come with locational attributes, temporal attributes, and maybe even a degree of additionality as well, that would kind of move beyond the current paradigm, which is largely based on like annually retired renewable energy certificates that can even be traded across borders. And so, if we can innovate in terms of that like energy attribute certificate side, ensure that those can be generated, traded, and retired appropriately, that will definitely help here as well.
Yeah, and that's definitely going to happen. I mean, we're seeing large corporate, data center owners and other large corporate buyers demanding this sort of hourly and locationally matched clean electricity to make sure that, they're basically canceling out their consumption. That if you're consuming a megawatt hour in this part of the grid, you've got a megawatt hour of electricity being generated in the same part of the grid at the same time, not somewhere far across the country or the state, or not some other time of the year that you're hoping kind of offsets your consumption later. We've shown in the case of both voluntary procurement for corporations and large commercial industrial loads, as well as for hydrogen consumers, that type of procurement is one of the most effective strategies to ensure that you don't have significant indirect emissions impacts on the grid, and you get your emissions footprint as close to zero as you can. I imagine that will be a viable strategy for direct air capture companies as they mature and get larger. I saw one of the questions the chat worried about, for kiloton scale facilities, it can be hard to do that, right? You're not gonna be able to sign these complicated power purchase agreements that involve, granularly tracked RECs and things like that. I think that's probably true at that scale, and I wouldn't necessarily lose a lot of sleep over trying to, sign contracts like that at that scale. But when you're talking about megaton scale, I do think you're going to need to be prepared for that sort of business strategy. And there, the development of these markets and these procurement strategies that are being driven by voluntary corporate buyers and by the hydrogen market, I think is going to pave the way quite nicely for the direct air capture market, because we've seen this happen before. The idea of a virtual PPA for renewable energy purchases, for example, was something that was very bespoke, very challenging to do. Companies like Google were doing it, but nobody else was. And then they sort of standardized that product, right? And they created a contract structure that's very very well understood now, and it's much easier for smaller actors to do that. And we also have these secondary markets for REC trading that you can sort of buy on the spot market that can help you, handle your mismatches. And that will likely occur for energy attributes, temporally granular energy attributes as well, that are, stamped with the hour when they're generated and not just the month or the year.
Let's dig in a little bit on both of those, because some of the folks on this call are going to be super familiar with power purchase agreements, some are not. So if we could just back up and just briefly talk about what are power purchase agreements, how do they work, and in what circumstances can you sign them and get them signed, and what circumstances can't you? And so that way people can kind of plan as they're starting to scale up. So whoever wants to field that one.
Yeah, I guess I can quickly just define, how I understand it, there's kind of three main types of power purchase agreements or PPAs. There's on-site, off-site, and virtual. An on-site PPA might be, you have like a commercial facility, you engage with a solar developer, and they pay for and own and operate the solar panels on top of your roof of your warehouse or something. And they handle all the capital costs, and you just agree to pay them, 7 cents per kilowatt hour or something for 20 years. That those panels are on. So it's on site, it's behind the meter, it's directly linked into your building's load. Then there's the off-site power purchase agreement. That's a little bit more complicated, where you, as an energy buyer, engage with the renewable energy developer. They construct a new renewable power asset somewhere. And then you agree to take the physical delivery of that power somewhere on the grid. So it's a little bit more complicated, but essentially it's the same structure where you lock in a price that might be constant, might be escalating for that power on a per kilowatt hour basis. And in exchange for that, you also get to retire the renewable energy certificates generated with that power. And then the virtual power purchase agreement, there is no physical delivery of the power. So the renewable power asset isn't on your site. You don't have to work with a power marketer to take delivery of that power, but rather it's just a financial contract where you have you in one place, some renewable power developer in another place, and you agree to pay them a fixed amount, or an escalating amount per kilowatt hour that gets generated. They sell it onto the grid. And then essentially how it happens is that you have like a locked in strike price. Maybe it's 5 cents per kilowatt hour. If they sell the power for 10 cents a kilowatt, or sell the energy for 10 cents a kilowatt hour, you actually receive the difference. Whereas if they sell it for less than the strike price, then you have to make up that difference. And in exchange for locking in that certain strike price for the renewable power developer, you get to retire the renewable energy certificates associated with that power generation. So it's a little bit more flexible, but it may not necessarily be in your same geography. And all of these different types of PPAs are viewed as more additional in general than just buying unbundled renewable energy certificates from the market. So that's just a quick overview of RECs and PPAs.
Yeah, maybe just to drill down to that last point a little bit more. The reason that they're likely to be more additional is that long-term contract that the renewable energy facility or clean energy facility, signs with you as an off-taker, that's critical for them to go to the bank and get the financing they need for this big fixed cost upfront investment that then, you're going to pay back over 20 years. You're all probably familiar with that same challenge, trying to get offtake agreements for the CO2 that you're selling, right? The captured CO2 that you're removing, without somebody who's willing to do an advanced procurement and sign up to buy that CO2 for a long period of time. It's very difficult to finance a facility. So it's the same kind of challenge for renewables developers, having those long-term contracts, that kind of certain revenue stream for at least most, if not all, of your power generation is usually a prerequisite, kind of a necessary but maybe not sufficient condition to go and finance a project. Whereas, if you're selling, renewable energy attributes or electricity on a spot market basis, where you've got significant volatility in your revenues, you're going to have to kind of heavily discount that, or have a much higher expected rate of return in order to pay back the riskier debt profile that you represent in that context.
Can you speak to how well that addresses, like how well doing something like this addresses second order impacts of diverting green energy, right? Because that's a big, big concern. It's a very hot button issue with regards to if we stand up a bunch of, megaton style sized DAC plants, that it's going to suck up all of the green energy, and we're actually going to be generating more, emissions overall in the grid. So how does power purchase agreements factor into all of this, and is it sufficient?
Yeah, so as I said, it's necessary in many cases, but not sufficient to show that the project that you're buying from would not have occurred if you didn't buy it. And that's really kind of the key counterfactual condition. You want to show additionality, right? That you're causing additional clean supply that is meeting your demand, and therefore, without your purchase wouldn't have happened. And so you're sort of making sure that as you add demand, you're also adding an equivalent amount of new clean supply. The challenge, and this is exactly what we've seen for corporate procurement and for hydrogen, is that, today, because of the low cost of renewable energy, wind and solar, and because of the subsidies that are in place in many parts of the world, it's just economic to go build lots of wind and solar anyway. I mean, the whole theory of the Inflation Reduction Act, right, is to provide the subsidies that just make wind and solar economic decisions for utilities and for, power purchasers and for developers all over the country. And so it's actually very easy in that environment to find an off-taker, to find a renewable energy supplier, sign the contract with them. That contract helps them go to the bank and get financed. But if you didn't sign it, somebody else probably would have, because it's a very attractive financial prospect. And so we see this in our modeling when we look at the kind of the system level interaction, accounting for changes in capacity, investment, and retirement decisions, that you can get a pretty easy 1-for-1 displacement where, either the wind farm that you helped get built would have been built by somebody else if you didn't buy it, or that wind farm is, built because you did it, but it's depressing electricity market prices and causing congestion in that region that prevents an equivalent project from not getting built. So the counterfactual world where your demand doesn't exist still would have had a wind farm in that same region, maybe built by somebody else. And this is a very tricky challenge, which is where the framework of hourly matching comes in, because the idea there is that, there are going to be some hours of demand when, I should say it this way. The idea there is that you're ensuring that every time you're adding 1 megawatt hour of demand to the grid, you're also ensuring there's a megawatt hour of added clean supply. And in many of the hours that you're doing that, the wind and solar projects would not have come forward anyway, right? You're going to have to do something else. You're going to have to add energy storage. You're going to have to add a more diverse mix of resources. And it's that additional action that ensures that sort of the overall clean mix is getting cleaner as you buy that demand. And it's a slightly different framework from the sort of offsetting by CO2, perspective. What you're basically just trying to do is mimic what would happen if you were plugged directly into a clean facility, right? If I was plugged into a wind farm, I would know that whenever I'm consuming electricity, it's coming from that wind farm. And on the grid, you can't really be assured of that. But if you're seeing renewable electricity or clean electricity injected into the grid in the same grid region at the same time that you're consuming electricity, accounting for losses in the system, you might need to procure a little bit more than you buy, then that is, functionally, physically the same as if you were plugged into the grid. And that's basically the best we can ask, I think, of electricity consumers. There's still this potential problem, which is just if there's a finite supply of wind or solar power or other clean electricity and you use it, like by definition, somebody else can't use it. But I think it's hard to hold developers of, data centers or or hydrogen facilities, direct air capture facilities, kind of responsible for a broader supply side constraint. Like we all just need to work together to relieve those supply side constraints, whether it's transmission bottlenecks or permitting delays or things like that. And so as long as you're making sure that you're kind of, canceling out your consumption on an hour by hour basis with clean electricity from the same grid region, I think you'd be pretty assured that you're having minimal, if not guaranteed to be zero, indirect emissions impacts. And we've shown that for corporate purchasers and for hydrogen. And I expect we'll see the same thing when we get into it with direct air capture facilities.
Great. Thank you, Jesse. Aniruddh, I know that we spoke a little bit about the potential option of having DAC companies anchor new renewable energy sources. And so I'd love if you could speak to that, because that also is a way to make sure that you're definitely not causing additional fossil fuel emissions.
Yeah, and I think the onus here really is on off-takers to try to set the rules for that, because I think it'd be unfair to expect a DAC company, trying to build out their technology and get it validated to think so far ahead on some of these questions. But if there are clear rules around how we think around indirect impacts of energy procurement for DAC, and off-takers are clear that they consider those seriously and they want that clean energy to be additional, then there's value to DAC developers going out and getting that energy at a premium. And enhanced geothermal, high temperature thermal storage are clear cases where you could incentivize new clean energy resources on the grid because of the demand for DAC. So DAC acts as a pull for this generation. And then, these resources can send energy to the grid when they're not supplying DAC, accelerating decarbonization compared to the counterfactual. We all want DAC to succeed and we hope it gets to gigaton scale, but there's a risk that it does not. But in this case, even in that scenario, we are still pulling these resources onto the grid, which helps us meet our decarbonization goals.
Yeah. All right. I think we're going to open it up to Q&A now. Ryan Anderson, I know that you had a question and you're up first.
Wonderful. Just scrolling up to find out what that question was. I've asked a couple. Hold on.
45Q and 45V, I think.
Yeah, yeah.
Looks like you had a couple others, right?
Yeah, that is it. And it really comes down to these three pillars modeling, three pillars rules around energy procurement for 45V. And if you expect your modeling to essentially show the same kind of rules are eventually going to be required to effectively produce, carbon negativity for 45Q for direct air capture.
I expect so, but we're still conducting that modeling now. I think it will. I think we have to be clear that there's just many different operating modes and designs for direct air capture, and so it may be a little bit more complicated an answer than it is for resources that are like dominated by electricity consumption. So some of the work that we've, preliminary work that we've seen for example, for thermal storage coupled systems, are that, because once you have that consumption flexibility, you kind of naturally want to consume when prices are lowest. That tends to already line up with the times when variable renewables are available. And so maybe that, it's kind of trivially easy to comply with that hourly matching, but also maybe not necessary, because your kind of natural incentive is to consume at the times when power prices are lowest. This would also be true, by the way, for electrolyzers if they weren't impacted by this large production subsidy of $3 a kilogram, which basically gives them the incentive to consume even when electricity prices are very high. If instead we had an investment tax credit, or we're otherwise sort of subsidizing just the fixed costs, then the break-even value of electricity consumption to produce hydrogen is maybe only $25 or $30 a megawatt hour. So you mostly want to consume when prices are low, and mostly when fossil generators are not the ones that would be called upon to meet your demand. But if you're willing to pay $100 a megawatt hour, or $85 a megawatt hour because you're getting this big subsidy, then you're willing to sort of keep chugging along. And so there may be some parallels there with 45Q, which is effectively it's a production subsidy as well. It's a capture subsidy. It pays you for capture and removal. It doesn't pay you for net system level emissions reductions or net life cycle emissions. And so that's something I think we need to keep in mind as well, as if you're in the context of a subsidy that's encouraging you to produce 24/7, then I expect that these sort of hourly matching requirements are more important than if you're in a context where you're trying to, you're technically capable of and economically incentivized to consume mostly when power prices are low. Those are just going to be kind of different circumstances.
All right, thank you. Next question is from Adam Gordon. Adam, if you're here, if you just want to unmute and ask your question.
Absolutely. Which one do you want? I asked a couple.
one of the first ones, I believe.
Okay.
Jason, is there a particular one that you wanted to
so-
ask about, or was it the business model one?
Yeah.
Yeah. So two of them. One is, obviously the whole usage and storage, utilization and storage is a big question in a lot of people's minds. And I'm wondering what you guys think about that in terms of, the future of DAC and its likelihood of adoption and cost and things like that, because that's all going to affect that. And the other was, and this is a little bit more ethereal of a question, but it seems to me that we can create business models such that DAC isn't used to offset and also encourages abating. So for instance, if you have customers for your DAC credits that are abating, they get a lower credit cost than customers who are just using it to offset.
Do you have an example of what that might look like?
Well, company A who is offsetting gets, $75 a ton of carbon for cost for a carbon credit, and company B who is only offsetting gets $150 a ton for carbon credit.
No, I mean, what do you mean by, like, what would an example be of somebody who is both abating and offsetting?
Oh, a company that is, actively working to reduce the amount of emissions they've got, and then the stuff that they can't abate, they offset.
I mean, that's what everyone should be doing, I guess.
Yeah, exactly. But it's not true today. And so I'm just wondering if you guys are thinking about business models that encourage that, sort of building in a carbon tax to the whole operation.
I mean, I can't think of a way you would do that as a direct air capture provider other than losing money, right, by selling at a discount. So
Yeah.
not sure where the additional revenue would come from to encourage that kind of behavior. But I think that's where regulatory processes are important, because, if you fast forward, you think about the role of carbon removal in a net zero economy. I mean, there's no way we can get to net zero unless we're, substantially reducing and mitigating direct greenhouse gas emissions. And then carbon removal is doing some small residual portion of what remains and sort of the most high value uses of fossil emissions or the most hard to abate sectors. And so, there's just no future where we continue business as usual fossil energy consumption and then make up the difference with carbon removal. So I think that's an area where regulatory processes and financial incentives from government and others are going to have to step in to make sure we're not doing that.
Well, I certainly agree that that's the best answer, but knowing that that may or may not happen, are there business models that encourage that kind of activity?
Yeah, I hear what you're saying, Adam, and I also am with Jesse in Jesse's boat in that I think it's got to come down from a regulatory perspective, because I could see, from Rory, your perspective, it's like, look, we're a small DAC company, we need to be able to survive, and we can't just offer pricing differences because we do. You probably have to charge whatever you need to charge in order to make it so that way your company is viable.
Yeah, I mean, I guess if you're in a sorry, I was gonna say, if you're in a beneficial position where you have a plethora of off-takers who are willing to pay a similar price, some of whom are also doing abatement, then you can choose as a company, I'm only going to sell to those ones, I guess. But that assumes they all have a similar willingness to pay.
Okay. All right. Thanks. And what about the utilization and storage question? What do you guys see as the future of that?
Sorry, Rory,
maybe I can
jump in.
Yeah, I can take that one. I mean, the sort of integrated assessment modeling that undergirds the sort of long-term assessment of pathways to net zero is incredibly clear that we need very large amounts of durable removal by mid-century, sort of in the gigaton scale, and really by the end of the century, potentially up to 500 billion tons. I think that means that even meeting that with all of the DAC companies and all the other carbon removal companies is a huge challenge. So if everyone ends up doing utilization, that is not going to get us there, I think. Certainly, I mean, if all the DAC companies, which, I think maybe 1 to 2 gigatons is realistic by 2050, we're not saying we get there, but it's maybe a realistic target for DAC specifically. That is still an enormously difficult challenge for the 120 DAC companies or whatever the number is now that exist. So, it's a collective challenge, and to get there, most of that will need to be stored. However, there is a real bottleneck for CO2 storage through to probably 2035. And, removals durable removals, at least those that want to put it into geological storage, are competing with point source emissions, which, in many cases, are giant elephants, and DAC companies are sort of relative mice running around the feet of those elephants. In the UK, you've got individual plants looking to do megatons a year. And then, and that's this side of 2030. There will be maybe 1 or 2 DAC companies, maybe 5 or 6 that are at a megaton scale by 2030, I would say realistically. So I think utilization presents in certain areas where there's less sort of moral hazard, like enhanced oil recovery, good near-term opportunities to help drive decarbonization of sectors. So that is decarbonization, right? Rather not perfect decarbonization. It's not, none of those processes are likely to be carbon neutral. They will probably still be net emitting processes, but they will be substantially better than if you are, if you're taking the equivalent, the CO2 from a fossil source. So I think that's a really important sort of near to medium term thing that people can and should do where the economics work. But ultimately, long-term DAC needs to be overwhelmingly, ultimately storing those tons with credits being the, I think the likely mechanism for revenue for those companies.
Yeah, I wanted to add to that in our net zero kind of modeling scenarios, that even in cases where you could use the carbon to supply remaining, say, liquid or gaseous fuel needs, from an economy-wide or emissions-wide perspective, if you think about it, I got to take a lot of clean electricity or energy to pull CO2 out of the atmosphere. Now I also need more clean electricity to make hydrogen and then assemble them in long-chain hydrocarbons to make synthetic jet fuel. That that consumes a lot more carbon-free electricity or energy inputs than simply taking the direct air capture and storing it and using it to offset some continued fossil jet fuel, for example. And, of course, there's other environmental impacts associated with continuing to extract oil for jet fuel. It's unclear if we can only, how do we reconfigure refineries to only produce, high value cuts like kerosene when you don't have much gasoline demand. So there's lots of challenges to that pathway too. But I think it's important to think about sort of the overall energy accounting and efficiency at that scale too. In many cases, it might make sense to just, and again, you don't have to do them in the same place either, have direct air capture somewhere in the world, right? Pulling CO2 out of the atmosphere wherever it's cheapest to do that. And you have the abundance of clean electricity. And then maybe you continue to use the highest value, petrochemical plastics, jet travel, those sorts of things that have a very high willingness to pay and are challenging to mitigate. Those may just continue to be from residual small amounts of fossil fuel extraction. That is something we often see. Unless we basically force the model to get rid of fossil fuels entirely, there's a lot of those sorts of durable applications in the end. Again, not anywhere like business as usual use of fossil fuels today, dramatic reductions in overall consumption, and only in the hardest to abate sectors that remains, not on-road jet, gasoline or diesel or things like that. The other thing I would say is we have to think about direct air capture and other chemical-based processes in competition with biogenic pathways for carbon removal, where if you're thinking about biomass gasification or Fischer-Tropsch liquids produced from bioenergy inputs, there you're basically getting both carbon-free or carbon-neutral fuel, and you can capture CO2 for negative emissions. Whereas direct air capture is always consuming carbon-free energy and only giving you the negative emissions. And so what we also often see is until you've sort of run out of your full allotment of sustainable harvestable bioenergy, DAC is behind that in line. Now, again, there's lots of logistical challenges. It's easier to put in a model than to build out in real time, in real life, all the ways to collect biomass feedstocks and get them to a facility and do it at scale. But it is worth remembering that you're always going to get more useful value out of a ton of carbon in biomass than you are out of a ton that you had to scrape out of the atmosphere.
Yeah, I mean, there's a really great following question that Christian, you asked in the chat. So
Thanks,
if you want to bring off mute and asking that, because I think it ties very deeply into what it is that we were just talking about. Christian, go ahead.
Thanks a lot. Thanks. And yeah, Rory and then Jesse started getting at this. So I guess it's a question for you, Jesse, is thinking, so a lot of our discussion started off smaller scale, which is we need to scale the tech, right? And then a lot of the PPA discussion, all these things are in the context of let's build DAC basically to suit the IRA, right? Let's get the US subsidies, let's build it integrated with our current power grid, like where there are people, where there's load, all these things, right? But if you think to 2050, right? A different vision for DAC is that it will look like, you know, the Chevron Gorgon project, right? It's like absolutely mind-boggling scale in the best place for it in the world, right? Where there's like natural gas, right? Or the Middle East power purchase agreement prices are already less than 2 cents a kilowatt hour for 2 gigawatt solar plants in the Middle East, right? And so do you see a future where DAC is developed in this sort of more Proximus setting of the US, but then outgrows that and turns into these mega facilities where it's really just about harnessing the cheapest possible renewable energy, and it's separate from a grid, it's everything. And then if that's the case, how would you think of your answer in terms of renewable fuels production, et cetera? Like, do you see a world in which energy is cheap enough to actually produce synthetic fuels to replace jet fuel and shipping fuel and all of these things? So think 2050 and forget about the grid, I guess, is the short version.
Yeah, great question. I mean, I do think that you're likely to see large scale DAC development around, you know, a combination of very inexpensive energy inputs, whether that's cheap wind or solar or geothermal or, you know, excess industrial waste heat that you can use for some of the lower temperature processes, right? You know, that's going to be one of the key draws. And then the second is you need somewhere to put the CO2 that's cheap, right? And so you're gonna have to be on top of good geologic storage locations or proximate to very large consumers of CO2, right? Because there just aren't that many that can consume CO2 at megaton scale, right? There's not that many processes that do that. You know, I do think that if I was just designing the system from kind of an emissions minimization perspective, we would see mostly removal and storage, not removal and use. But I do think another angle that I didn't really talk about before is just sort of the social license aspect. I can imagine aviation company, you know, United or whoever else, being much more comfortable saying we've made sustainable aviation fuel that we're burning in our engines than we're continuing to use fossil jet fuel and we're paying for this giant facility in the UAE that's sucking CO2 out of the atmosphere and putting it in the ground, right? Even though that might actually be better from an overall emissions perspective, just because I think, you know, the sort of offsetting framework is one that's harder to sell to people, hard to explain. It feels like cheating or something. And, you know, and there is still negative environmental impacts from fossil energy extraction, even if it's offset from a CO2 perspective. And so it may be that we continue to see a premium put on these synthetic fuels for aviation, for shipping, you know, for bioplastics or other things that will make use more attractive from a social and economic perspective, even if from a kind of total energy inputs perspective, we could get more CO2 reductions by taking all the energy we use to make that synthetic fuel and just use it to displace more fossil fuel somewhere else in the world, or to you know, to more rapidly reduce emissions. So I don't know where that's going to go. I think that's one of the ones that's going to be an interesting, you know, social license question that could play out in the future.
That's great. And actually longer term energy security is a topic in Europe, et cetera. Do you also see a sort of geopolitical strategic angle where actually you would want to produce synthetic fuels in Europe or in the US to not be importing it from far away, or do you model that in any way?
If you don't think you're going to continue to produce any fossil fuels, then maybe. But I think, you know, like the reduction in fossil fuel consumption means that, you know, Europe and most places should be able to be secure, right? With some residual amount of fossil, you know, production for their remaining needs, because it's such a dramatic reduction from what they're consuming today. But it's hard to know. Again, like there are network economies of scale to the fossil energy extraction industry too. If you start chipping away at it, the whole thing might collapse. And so it you know, it's not necessarily true that you can just, you know, only produce jet fuel, right? That's a very different refinery and a very different supply chain than the system we have today. And maybe if you do that, jet fuel gets really expensive, and then it is better to just do direct air capture and synthetic fuels. So these are the kinds of questions that I've been trying to think about going forward. And you know, I think they're really open questions to play with.
Thank you. Ani, I know you've been very active in the chat answering various folks' questions, but in terms of the questions that you've answered so far, are there any that, you know, make a difference to elaborate on verbally? And if you could just repeat the question that you're answering and then dig in, that'd be great.
Well, there were a couple of questions about energy use and general like energy efficiency and low cost clean energy. I think clean energy will be abundant, hopefully, you know, 10 years from now, but there are a lot of industries that are going to be competing for that low cost clean energy. And so even though you're at the kiloton scale now and you're trying to validate your technology, I think it's really important for DAC developers to start thinking long term and start building these relationships, because connecting to the grid and getting megawatts level of clean power. You're competing with data centers, energy storage, other industrial users who are all looking to buy that cheap, clean energy. So building those relationships early is going to be very important.
Yeah, maybe add to that. I think there was a question earlier on about how do DAC companies in the near term procure, get the energy that they need. And as it comes back to this point I made at the start about the appropriate partnerships, we've seen a lot of action kind of from hydrocarbon sort of energy companies in DAC in the last couple of years, but maybe have seen less on the renewable energy side. And I think as DAC starts to scale, as there are new projects being brought online, I think it would be very interesting that, and I think we will likely see more renewable energy companies engaging with the direct air capture sector. I think maybe the other thing to say is, it shouldn't be on individual DAC companies to be working out how to do those small, when you're a mouse, it's kind of difficult, right? Like to get access to those big things. So the way that the UK is doing it, which I think is a really good model, is they've got these net zero clusters, they're cross-sectoral. They want to kind of take a portfolio approach to say, we'd like to build some direct air capture into the, along with power BECCS and hydrogen and some of these other things. And so they'll kind of reserve space. So, we will be selecting clean energy that will go into that cluster. If you are a DAC plant, you will be able to access that, that clean energy as well as that pipeline. And I think there's an opportunity here. That's why I love what Deep Sky is doing and what, there's other people sort of working on this, which is, DAC sites which are being developed by a project developer where they will aggregate a few different DAC companies so that the DAC companies don't have to do all the project development themselves, so that you can get on the sort of deployment, get on the field, actually be selling credits in a way that doesn't mean you have to jump to megaton scale, take huge amounts of commercial risk, have massive challenges with your financing when you've still got big, technology risk. You get in at the sort of kiloton scale, low single-digit kilotons, maybe double-digit kilotons. Get on the field, start to demonstrate, get your revenue in, and then maybe the next step for you is thinking about how to sort of develop sites where you are more involved as a project developer. So I think that more of people like Deep Sky and some of the other people thinking in that concept, and I know there are a few out there, would be really welcome, even governments too. So that, in Scotland, they're developing kind of DAC Innovation Park with sort of similar-ish concept, although maybe slightly earlier TRL. So I think we'd be great to get a bit more of that stuff, emerging in the next couple of years.
Right. Awesome. Thank you to all of our panelists. Jason, I know you've got a couple of announcements before we head off, so I'll pass the mic over to you.
All right. Thank you, Adina, and thank you to our panelists. And most of all, thank you to you, our audience, for being with us today. I really appreciate it. Added the panelist contact information. If you want to get in touch with people afterwards, goodness knows, plenty of questions came up in the chat. We might not have gotten a chance to answer them all, so feel free to reach out if you want. Also, a couple of announcements. One, let us know how we did today in our post-event survey. Email will be in your inbox shortly, but I've also added a link in the chat. Good, bad, and different, especially the bad or indifferent. We want to hear how we can improve our events for you so that we can present things that are going to move the carbon removal industry forward. And finally, our next event is going to be in a week's time. We're going to be talking about marine CDR permitting and siting with an excellent panel then talking about how to unlock getting projects in the water for marine carbon dioxide removal. So with that, I just want to once again say thank you to Adina for moderating. Thank you to our panelists. Thank you for staying with us. And we wish you all a good day